Let us now look at some of the characteristics of radio waves, starting with frequency, represented by the letter F. We know that electric fields flowing out of an antenna follow a wave pattern, and this is called a sinusoidal wave. Each complete pattern of the wave is called a cycle. The time it takes for each cycle to be completed is called the period, represented by the Greek letter tau. Because radio waves are so small, the time for each cycle is measured in microseconds, that is, 1/1,000,000th of a second. This is expressed as 10 to the power of -6, written as μs. The number of cycles per second is known as frequency and is measured in hertz. The device used for displaying frequency is the oscilloscope. Move the slider to see how wavelength and frequency are inversely proportional to each other. So, if one cycle of a radio wave takes 1 second to be completed, the wave will have a period of 1 second and a frequency of 1 hertz. If there are 1,000 cycles per second, the wave will have a period of 1/1000th of a second and a frequency of 1,000 hertz. If a radio wave takes 1/8 of a microsecond to complete, one cycle, that is 0.125 of a microsecond, we can see that it has a frequency of 8 million cycles per second, or 8 million hertz. Because these figures for radio wave frequencies are always so large, they are expressed in a more convenient way as kilohertz, megahertz, or gigahertz. Kilohertz are units of 1,000 cycles per second, that is, 10 to the power of 3. Megahertz are units of 1,000,000 cycles per second, that is, 10 to the power of 6. Gigahertz are units of 1,000 million cycles per second, that is, 10 to the power of 9. So instead of saying that a radio wave has a frequency of 8 million cycles per second, we can now say that it has a frequency of 8 megahertz, written as you see on screen. The wavelength, or length, of a radio wave cycle is the distance between the start and the end of the cycle, generally shown as the distance between the peaks of two successive identical waves. It is denoted by the symbol lambda. The number of times that a wave is repeated during a second has a direct correlation with its length. The longer the wave, the fewer there can be in a second, and the shorter the wave, the more there can be in a second. In other words, wavelength and frequency are inversely proportional to each other. Therefore, wave frequency, measured in hertz, and wavelength, measured in meters, are directly related, and we need to be able to calculate one from the other. The formula for calculating wavelength, lambda, is the speed at which a radio wave travels, c, divided by the frequency of the wave, f. In order to be able to do these calculations, we need to recall that radio waves travel at 162,000 nautical miles per second, or 300 million meters per second. This figure in meters per second is the one to use in all calculations. If the period of a wave is given, but not the frequency, we need to convert the period of the wave into its frequency. If the period of the wave is 0.125 microseconds, that is 0.125 or 1/8 of a millionth of a second, then we need to express this in terms of a whole second, which is 8 times 10 to the power of 6. Each wavelength can be calculated by dividing the distance that all radio waves travel in a second, namely 300 times 10 to the power of 6 meters, by the number of cycles or frequency of our radio wave in a second, namely 8 times 10 to the power of 6. We can cancel out both figures 10 to the power of 6, leaving us with 300 divided by 8, which is 37.5 meters. So if the frequency of the radio wave is 121.5 megahertz, that is 121.5 million cycles per second, divide the speed of the wave by its frequency, which equals 2.47 meters. The formula for wavelength is simplified to 300 divided by frequency in megahertz, giving an answer in meters. You may need to convert the data given from kilohertz or gigahertz into megahertz. Let's try one more, but this time we know the wavelength, 1,515 meters, and we want to find the frequency of the wave. Transpose the formula so that frequency is the speed of radio wave divided by the wavelength, which is 198,000 Hertz, or 198 times 10 to the power of 3, which we call 198 kilohertz. Because we always cancel the common figures of 10 to the power of 6, these two formulae can be shortened. The formula for frequency is 300 divided by wavelength in meters, giving an answer in megahertz. You will need to convert the wavelength into meters if the wavelength is given, say, in centimeters. Radio waves of different frequencies are used for different purposes. For example, low-frequency waves of between 30 and 300 kHz and with a wavelength of between 1 and 10 kilometers are used in long-distance navigation aids, such as the non-directional beacon, the NDB. At the other extreme of the frequency bands are super high-frequency SHF transmissions with a frequency of between 3 and 30 gigahertz, that is 30,000 million cycles per second. SHF radio waves are used in short-range radars, such as airport vehicle and aircraft ground movements. They have a wavelength of between 1 and 10 centimeters. Unfortunately, you must learn these frequency band details for your examination. Note that each band is greater in its number of hertz than the previous one by a factor of 10. There are 3 kilohertz bands, 3 megahertz bands, but only 2 gigahertz bands. You may find this mnemonic useful in remembering the sequence of frequency band names. Volume high, very useful. Try some of these calculations. They are similar to the ones you will be asked in the examination. Click on the empty boxes to reveal the correct answers. If your answer is wrong, You may have used the incorrect formula, or you may not have converted the data into megahertz or meters. When considering sinusoidal waves, such as that of a radio wave or an alternating current, it is convenient to be able to denote a particular point or phase on the sinusoidal waveform. We also need to know that the amount by which the wave moves away from its zero or start position is called amplitude. Sinusoidal waves are constructed by tracing the progress of a given point on the circumference of a circle. The 360 degrees of a circle are used to represent an equivalent position on the sinusoidal wave. The start point of the cycle, the zero phase point, always lies on the zero amplitude line at the start of the positive half of the sine wave, that is, the part above the zero line. The part of the wave below the zero phase line is called the negative part of the wave. The peak of the positive amplitude is at 90 degrees. As the wave passes down through the zero line, this is 180 degrees. The negative peak of the amplitude is at 270 degrees, and the wave finally returns to 360 degrees or zero. Turn the dial on the screen to rotate the circle by a chosen number of degrees and create the corresponding sinusoidal wave phase. Some radio navigation systems, for example the VOR, use the comparison of phase between two signals to define navigational information. This is only possible when the two signals have the same frequency. Otherwise, phase comparison would be meaningless. One wave is designated the reference wave, and the other is designated the variable wave. Identify the zero phase position of each wave. This is the point on the zero phase line where the wave starts to move above it. Then see where the zero phase of the variable wave lies in the waveform of the reference wave. In this example, we see that the variable wave is at 90 degrees phase difference from the reference wave, or put another way, it is 90 degrees out of phase. In this example, the variable wave is at 135 degrees phase difference, and in this example, it is 315 degrees phase difference. This brings us to the end of our description of radio waves, in which we have considered wavelength, frequency, frequency bands and phase notation, and phase comparison.